Today we start a new part of the course, which is radiative transfer between surfaces. So far we have looked at emission by black bodies and the radiative properties of real surfaces. Now, we are ready to ask this question: what fraction of radiation leaving a surface actually reaches another surface? Now, this is a very important issue in engineering application. You would like to know of the radiation leaving a flame, what fraction reaches a certain wall of a boiler, or you would like to know of the radiation leaving a certain wall of an enclosure, what fraction will reach another wall. So, this problem is one of geometry, three-dimensional geometry, because as you know, radiation leaves a surface in all direction, all the 3 dimensions, and we would like to know what fraction actually reaches another surface in order to calculate the radiation impinging on the surface. So, this problem is fundamentally a geometry problem, purely a 3-dimensional geometry problem. But if the radiation leaving a surface depends strongly on angle, then not only geometry is an issue, you also have to worry about the directional properties of the radiation emitted or reflected by that surface. But there are many examples in real life where one can assume that the surfaces we are dealing with are diffuse isotropic emitters and reflectors. In such a case, we will show that the geometry part of the problem gets separated from the radiation part of the problem, and that makes life somewhat easier. So, in today's class, we will define what is known as geometric configuration factor. So, this factor is a very important quantity. It tells you what is the fraction of radiation that leaves one surface and reaches another surface, and under certain conditions, this is purely dependent on geometric configuration of the two surfaces and nothing else. So, it makes the analysis of radiation problem somewhat simpler, because you can separate the radiation part of the problem and the geometry part of the problem easily, and you will see examples where this makes our computation somewhat easier. But of course, if you are unlucky and the surfaces you are dealing with are not diffuse isotropic, then the geometry and the surface properties get entangled, and you have to do a very complicated kind of analysis. So, if you encounter such conditions where the properties of surfaces are pretty complex function of angle, then the approach we are going to recommend discuss in the next few lectures may not be that useful. You may be better off using what is known as Monte Carlo. We will discuss these Monte Carlo methods near the end of the course. These methods actually follow every photon that is emitted or reflected by a surface, and follow the photon till, if it is reflected, it will follow the photon after reflection, and ultimately until the photon is absorbed in another surface. So, today, because of the availability of high speed computers, it is possible for you to follow millions of photons from their birth and their subsequent reflection and absorption, and you can do the life history of all the photons and compute the total radiative flux. So, this method is very computer intensive, but has the advantage that it can deal with any complex geometry, any complex situation. But you would not resort to these techniques for simple problems, which we will deal with in the next few lectures. For that, you should be quite satisfied in using the geometric configuration factor. Okay. Now, let us now look at the example here. So, we want to ask of the radiation leaving the surface dA1 elemental surface, what fraction reaches the surface 2 dA2. Okay. So, radiation is leaving the surface and a certain fraction is intercepted by surface dA2, and what fraction of the radiation leaving surface 1 is intercepted by surface 2 depends upon the orientation of surface 2 with respect to surface 1, the distance between the two surfaces. So, it depends on the distance S, that is the distance between the center of the surface 1 and surface 2, and also the angle theta 2 and theta 1. These are angles between the line joining these two elemental surfaces and the local normals. These are local normals. Now, we will derive that expression which tells you what fraction radiation leaving the surface reaches the surface. After that, we will ask under what condition this quantity is a purely geometric factor, and we will show that if the radiation leaving the surface is diffuse isotropic, that independent of angle theta 1 and phi 1, then we will show that indeed this fraction is a geometric factor, and that makes our life very easy. So, it is a purely geometric problem, and then in the next few lectures we will discuss techniques of calculating this factor purely from the geometry of the problem. There are several interesting techniques available to calculate this factor, and we will go through those techniques. Now, let us derive this expression for geometric factor, and so now I will draw a simple figure to remind you of that situation. So, let us say call this now surface dA1 as a normal, this is surface dA2, it has a certain normal, and the line joining them is your distance z, and this is theta 1 and that is theta 2. So, angle between the line joining these two surfaces and the normals of these surfaces. And if you ask what is the solid angle subtended by surface 2 and surface 1, by definition of solid angle, d omega nothing but area projected of surface 2 divided by the distance s squared. So, this is a solid angle subtended by surface 2 in surface 1. Now, let us ask what is the energy radiation leaving surface 1. Okay. Radiation leaving surface 1 this from the definition of intensity is I prime lambda 1 surface 1 cos theta 1 d omega 1 d lambda. This is the radiation leaving surface 1 in that direction towards surface 2, and radiation that leaves 1 which arrives in surface 2 is this times the solid angle subtended by surface 2, which is d omega 2 cos theta 2 by s square. Okay. So, this is the solid angle that is subtended by 2 in 1. Okay. So, as a matter of fact, now I do not have to keep this because I have defined what d omega 1 here. Okay. So, so this is solid angle subtended by, so this, let me rewrite that for convenience. So, we wrote this as d omega 1, this can be further expanded to I prime lambda 1 cos theta 1, and d omega 1 I take it from there cos theta 2 cos theta 2 dA 1 dA 2 by s square. Okay. So, this is the radiation that is leaving 1 and reaching 2. Okay. This is radiation leaving 1 and reaching 2. Now, let us ask this question: what is the total radiation leaving 1 in all directions? If we take all directions and integrate to all directions, then radiation leaving surface 1 in all directions is nothing but pi times I prime lambda 1 dA 1 d lambda. Okay. While doing this integration, we are assuming that radiation leaving 1 is diffuse isotropic. Only then you can calculate this quantity. Okay. Without assumption of diffuse isotropic this quantity is function of theta and phi, you can integrate. If it is diffuse isotropic, then you can integrate, get the answer. Now, we say what is the fraction of radiation leaving 1 and reaching 2? Leaving 1 and reaching 2. That is the definition of F dA 1 dA 2. So, now we will write down what the expression says. So, F dA 1 dA 2 equals, what is the radiation leaving 1 and reaching 2, that is the numerator, this is what we saw just now. This is the radiation which leaves 1 reaches 2 divided by radiation leaving 1 in all direction. This is so you can see that I prime lambda 1 will cancel out here. Okay. And so will d, I am sorry, this is d lambda, I am sorry. So, d lambda also does not play any role here, d 1 also cancels out. So, we get a simple relation for differential geometric configuration factor as nothing but cos theta 1 cos theta 2 by pi s square. Okay. That is the dA 2, of course, the dA 2 is not gone, the dA 2. So, you should notice that this is a non-dimensional number because it is a fraction, this is non-dimensional because it represents a fraction and it depends only on the angle theta 1, theta 2, area of surface 2 and the distance. Okay. So, it is a very simple relation. Now, this relationship has some interesting features. Notice that dA 1 f dA 1 dA 2 will be equal to cos theta 1 cos theta 2 dA 1 dA 2 by pi s square. So, this is a symmetric function. You can interchange theta 1 theta 2, it does not change. Therefore, by symmetry is also equal to dA 2 f dA 2 dA 1. This is known as reciprocity. The reciprocity is a very important property telling you that the total radiation leaving 1 and arriving at 2 are the same as leaving 2 and arriving at 1. And so, this will be very useful because if you are able to calculate this quantity, then you also know this quantity because it depends only on the area ratio. Now, this geometric configuration factor between differential areas requires only one condition, that is you are dealing with diffuse isotropic emitters and reflectors. Okay. So, once you made that assumption, this geometric factor comes out naturally. So, as long as the radiation emitted and reflected by a surface is diffuse isotropic, then you are guaranteed that the relation between the radiation leaving surface dA 1 and reaching surface dA 2 is a purely geometric factor. But as you can realize, this equation, although very useful, is not very practical, because in applications in engineering you need not f dA 1 dA 2, but you need f A 1 A 2, that is the geometric configuration factor between finite areas. So, this quantity is a quantity that really of great interest to us. Now, the question is, we have just shown that the geometric configuration factor between differential areas is completely a geometric factor if the surfaces emit and reflect in a diffuse isotropic fashion. But is that condition sufficient for calculating this factor between finite areas? The answer is no. You have to apply some more conditions. Why is that? Because if you look at the definition, if you want to calculate between finite areas, then you have to integrate over the two surfaces A1 and A2. This intensity leaving surface 1 cos theta 1 cos theta 2 dA1 dA2 by S square. This is a quantity enumerator. In the denominator, you are looking at pi times what is the total radiation leaving surface 1 . Now, if you look at this general expression for the geometric configuration factor between finite areas, you find that this will be a purely geometric factor only if I prime lambda not a function of space in A1 and A2. Okay. If the intensity leaving surface 1 is varying with space, then you are in trouble. Then this integration, you cannot take out this term out of the integral. If you want to take this term I prime lambda 1 out of the integration, then it should not be a function of space in 1 and 2. Now, when will that happen? It will happen if emission is uniform, reflection is uniform, does not vary with space, and finally, incident radiation is uniform. So, only then you can guarantee that this quantity is independent of angle, independent of space, and you can take it integration. Then this also comes out, and then you have a simple expression. Now, this is not commonly met in real situations, especially the condition that the incident radiation should be uniform is rarely met, because most surfaces you are dealing with get radiation from all directions, and the radiation coming from different surfaces impinging on a given surface will not be uniform. So, if the incoming radiation coming on a surface is not spatially uniform, then there is very little chance that the radiation leaving the surface will be uniform in space, even though the properties of surface like reflectivity are uniform. Even then, because the incoming radiation is non-uniform, the reflected radiation will be non-uniform. So, you must remember that this condition finally we get for F A1 A2. Once you remove the I prime lambda, is simple A1 A2 cos theta 1 cos theta 2 dA1 dA2 by pi, sorry, S square is there in the numerator, by pi A1. Okay. You can write it more neatly as 1 over A1 integral A1 to A2 cos theta 1 cos theta 2 dA1 dA2 by pi r square. So, this is now a truly geometric factor. It depends on the relative orientation theta 1 theta 2 of the two surfaces, and this is a very useful quantity to have, but remember this is useful only if incoming radiation is uniform in space, and secondly, surface properties like emissivity and reflectivity are invariant in space. So, you want radiation to come uniformly on that surface, and the surface properties like emissivity and reflectivity should also do not vary in space. So, this condition is not met commonly in many practical applications. So, you have to keep that in mind, that use of geometric configuration factor between finite areas is not always valid unless you have a annual condition that the incoming radiation is uniform spatially and the surface properties like emissivity and reflectivity do not vary in space. But if you are lucky and these are satisfied, then you can use this factor. Now, you can also see from the symmetry of this particular equation, you can also see there are following conditions satisfied. A1 F A1 A2 equals A2 F A2 A1. This is called reciprocity. So, this is a very useful property. If you happen to get hold of F A1 A2 from some source, you also know F A2 A1 immediately. So, it helps you generate new shape factors or geometric factors based on available values. So, this is a basic parameter which you will be now studying in the next few lectures and trying to understand under what condition these can be applied and what are the real life examples where this can be implemented. Now, in today's computer world, in principle, this integration which we talked about this integration can be done on the computer, but you must recall that although this can be done on the computer fairly easily, but it is important for you to actually tabulate correctly the limits of the integration, because that the computer will not know. You have to indicate what are the limits of the integration A1 A2, and once you have given those limits, of course, there are many software packages which will do the integration for you. But for simple geometries, these configurations already been done and given in various tables in books. So, we will take a few examples to illustrate the values of geometric factors. So, very common geometries which are encountered quite often in the real world are quantities for which integration has already been conducted and the relationship is already available to you. And one example that we will now look at is the now let us look at this example here between a small area dA1 and this long element here. So, f dA1 dA2 is fairly well defined quantity from the definition we are given there. Now, you need to integrate over this length to get the configuration between an element dA1 and a strip A2. Okay. So, that is our interest, and in this case the basic dA1 dA2 we know from the definition, but we need to integrate over one of the elements, that is the element dA2, to get a relation between f dA2 to strip 1. Okay. Now, this integration can be carried out fairly easily, and this is a purely a geometric problem. So, I will now write down a few steps indicating how this integration is done. Okay. So, we will look at the integration from this is now area f dA1 to A2. A2 is the strip that you are looking at. So, you can look at the basic geometry of the problem, and wherein the distance, the normal distance between two elements. So, one element is here, that is dA1 here, and the other element, if you look at the end view, is here, and this projected distance between these two is L. Okay. This is not the 3-dimensional distance, this is distance projected normal to the to this plane here. So, you can do all the simple geometry that this calls for, and one can easily show that, and this angle between the normal to the surface and this is beta. This is not theta 1, theta 1 is the 3-dimensional angle. So, if you go back to the picture, you can see theta 1 is the angle when you draw the vector S joining dA1 and dA2, while beta is the projection of this on this plane. Okay. And so, that is where you get beta, and once you know that beta and this distance L, so L cos beta is the vertical distance here, and so we will now use the geometry, and I will stick to notation in the figure. So, I will draw this small L cubed cos beta. This is a purely problem in geometry by pi, and then you integrate in the x direction from minus infinity to plus infinity, that is normal to the plane of this board, and that will come out as dx by L squared plus x squared the whole square. Now, all of you can do the integration, that is fairly straightforward, and you will get this answer now as cos beta d beta by 2. Okay. So, this is a very simple result indicating that the geometric factor between the element dA1 and a finite area A2, which is the strip, is nothing but cos beta d beta by 2. Can also be written as half of d sin beta. Now, you can go further and ask the next question as to what will happen if you now integrate over both A1 and A2, okay, and that result is of relevance later, and we will examine that issue when we look at the geometric factor between two surfaces which are infinite in one direction, that is, they are very long in one direction. And so, we look at the such examples do occur in practical situation where one dimension may be in a furnace or some other situation, or a cloud where one dimension is very large compared to the other dimension. Then the problem is essentially two dimensional, but remember that in radiation the basic phenomena is three dimensional. Although one dimension is long compared to the other dimension, you still have to take into account the three dimensional nature of the phenomena, which you cannot ignore. Okay, and so that issue we will now address in our example. Now we will take up, and the issue we are going to address is how to calculate geometric configuration factor in those situations wherein one dimension is extremely long compared to the other two dimensions. We want to know whether some simplification is arrived at which will enable us to calculate things without actually doing the integration. Okay. And this method is quite useful and powerful, and as a simple interpretation in terms of energy. Okay. So, we will look at that example now, and to do that I will take a simple example of a triangular system. Imagine we have a triangular enclosure. A1, A2 and A3. So, all dimensions perpendicular to the board are very long, are infinite. So, you are looking at a problem where this dimension is extremely long compared to what is there in this plane, and the question is, such a configuration, does it simplify your problem? Now, we will appeal to reciprocity and see we know f A1, A2, f A1, A3. We want to calculate these quantities without actually performing an integration. We want to calculate these quantities without actually doing integration of the equation. Now, it is possible because we can write down energy balance, radiation leaving surface 1 and reaching surface 2, as well as radiation leaving surface 1 and reaching surface 3 has to be equal to radiation leaving surface 1. So, this shows that f A1 A2 plus f A1 A3 equals 1, because these are all plane surfaces, and a plane surface cannot see itself. So, for a plane surface, that is which are not concave, f A1 is 0. So, this is called as self-viewing factor. So, a self-viewing factor is the fraction of radiation leaving a surface which comes back to itself. Now, this can happen only when the surfaces are concave. The surfaces are plane or they are convex, they cannot see themselves. So, self-viewing factor is 0. So, we are considering a case where all the three surfaces A1, A2, A3 are completely. So, this surface A1, A2 and A3, all three surfaces are non-concave and therefore, f A1 equals f A2 equals f A3 equals 0. So, they do not see themselves. Now, let us write down the first law for each cases. The radiation leaving surface 1 reaching surface 2 or leaving 1 and reaching surface 3 equals 1 by first law, because whatever reaches 1 has to reach 2 or 3, there is no other way, and this dimension is infinity. Similarly, f A1 plus f A3 equals 1, and of course, f A1 plus f A2 equals 1. So, we have 3 equations here with 6 unknowns, right. So, you can't solve for all these values, but we know reciprocity, which is A1 f A1 A2 equals A2 f A2 A1. Similarly, A2 f A2 A3 equals A3 f A3 A2, and finally, A1 f A1 A3 is equal to A3 f A3 A1. So, now we have 6 equations. In 6 unknowns. So, you have remind you there are 6 equations in 6 unknowns, and hence you can solve this problem completely without doing any integration. You require no integration to be done, that is that, which is quite complicated. So, in such a situation, the results are very simple. You can just eliminate what you do not want, and the key point I want to remind you is that this simplification implies that this integration is not required. This integration is fairly complicated and will take a lot of time and effort. So, if you encounter a situation with 3 surfaces which form an enclosure, and so we want to say that if there is a 3 surface enclosure, with non-concave surfaces, then you can show that F A1 A2 equals A1 plus A, okay, sorry, A1 A2 plus A3 minus 2A1 A1 plus A2, just a minute, okay. If you want to write F A1 A2, it is A1 plus A2 minus 2A3, I am sorry, A1 is A1 plus A2 minus A3 by 2A1. So, the configuration factor between two finite areas A1 and A2, if they are part of an enclosure containing 3 surfaces and all surfaces are non-concave, it is sum of the area of the 2 surfaces involved in the interaction minus the area of the third surface divided by twice A1. Similarly, you can write the other two, F A1 A3 is A1 plus A3 minus A2 by 2A1, and this is a very powerful result, because you have avoided all integration. You need to know only the surface area of the 3 surfaces. So, that is fairly easy quantity for surfaces of known shape. So, you have managed to avoid the difficult 3-dimensional integration that is usually called for. So, this is a very powerful result, and so this can be used in situations where one dimension is very large compared to other 2 dimensions. So, the problem becomes essentially a 2-dimensional problem, but still the integration that you have to do is 3-dimensional, but you avoid the integration by appealing to law of conservation of energy and reciprocity. So, combining energy conservation and reciprocity, you get this relationship between the shape factors, and this is a very useful result, and it has applications which we can adopt very easily. Now, there could be situations where you actually do not have 3 surfaces, but you can always construct an 3 surface enclosure, even though, let me take an example. Suppose there are 2 parallel plates, maybe a furnace for example. One is surface 1 and the surface 2, and the distance between the plates is d, and this dimension, the dimension normal to the board here, is infinity. Question is, can you calculate F A1 A2 without actually doing any integration? That is the issue. Now, the way we will do this is, we will construct an enclosure. You have surface 2 here, surface 1 here. You draw a dotted line, this is an imaginary surface. You draw another dotted line, that is also an imaginary surface, right. So, this surface 1, let us call this surface 3 and let us call surface 4. Okay. Then we apply the rule we just derived to this triangular enclosure. Three, 4, 1. Okay. And what do we know from this? From our earlier formula, we know that A1 F A1 to A3 is equal to area 1 area 3 minus area 4 by 2A1, right. Similarly, you can construct another triangle here. So, let us call this as 5 and 6. So, we can also say A1 F A1 A6, okay, is equal to A1 plus A6 minus A5 by 2A1. So, I have constructed two triangles on the same base of surface 1 and applied the triangle rule for non-concave surfaces and arrived at two expressions. Now, what I really want is F A1 A2, that is what I want. I got F A1 A3, I got F A1 A6. Now, I can apply first law of thermodynamics. So, for this enclosure I can say radiation leaving 1 reaching 2 plus radiation leaving 1 reaching 3, radiation leaving 1 reaching 6 has to be equal to 1. Therefore, the quantity I want is F A1 A2, it is 1 minus F A1 A3 minus F A1 A6. So, this is from first law. This first law. Now, we already derived expressions for these two. So, we can write F A1 A2 equals 1 minus F A1 A3, if you recall, was A1 plus A3 minus A4, which was this quantity, by 2A1 minus A1 plus A6 minus A5 by 2A1. So, we have been able to get the configuration factor between surface 1 and 2 in terms of just the areas of 1, 3, 4, 5 and 6, and these can be easily calculated, and since this dimension is infinite in this direction, all these are essentially lengths of various surfaces here, okay. And you can see here there is a minus half here, there is a minus half here, the one will cancel out. So, finally, you are, let me go to that, we just write down and then we go next page. You can see that this and this will cancel out and we can add 4 and 5, okay. So, we will get A4 plus A5 minus A3 plus A6 whole thing divided by 2A1. So, it is a very simple result which has several physical insights. So, in the next lecture we will proceed further in using this method So, what we did in this lecture is define a quantity called geometric configuration factor, which is a purely geometric factor if applied between finite areas, if the radiation leaving that surface is uniform in space. And then we showed that for certain situation in which one dimension is very long compared to other, there is a simple way to evaluate this geometric configuration factor without actually doing the integration. So, we will in the next lecture look at how this simplification helps us to solve some interesting problems.